Imagine boarding a spacecraft bound for Mars, knowing you'll never return to Earth. Sounds like science fiction? In fact, this is the brutal reality every future Mars astronaut faces. According to current scientific understanding, it's virtually impossible for humans who travel to Mars to ever live on Earth again. The reasons aren't a lack of rockets or technology, it's the human body itself that becomes the biggest barrier. The journey to Mars is one of the most extreme undertakings humanity has ever attempted. While it took us only 3 days to reach the Moon, a trip to the Red Planet takes between 6 and 9 months each way. This means astronauts will be away from Earth for a total of 2 to 3 years before they can even think about returning home. 2 to 3 years during which their bodies will be subjected to unprecedented stress. And the distance is just the beginning of the challenge. At approximately 55 million kilometers, Mars is so far away that even light signals take over 20 minutes to reach Earth. An emergency evacuation? Impossible. A medical emergency? The nearest hospital is 8 months away. These astronauts are on their own like no humans before them. But the real drama lies not in the distance or the isolation. It lies in what happens to the human body during this journey. A Mars mission means the body is exposed to 3 completely different gravitational environments. First, weightlessness during the months-long journey. Then, the reduced Martian gravity with only 38% of Earth's. And finally, if a return is even attempted, the full gravity of our home planet. Each of these transitions is an extreme challenge for our bodies. But the interplay of all 3 over a period of years has consequences that are still not fully understood. What scientists do know, however, is alarming. The human body is optimized for life on Earth. If we remove our bodies from this environment for an extended period, a gradual process of change begins. A process that, after a certain time, becomes irreversible. Astronauts who have spent months on the International Space Station often need weeks to be able to walk again after their return. Their bones have become porous, their muscles weakened, their hearts deteriorated. And this after only 6 months in Earth orbit, where rescue is always possible and Earth is only 400 kilometers away. On a Mars mission, this time frame at least triples. And returning home is not an option. The following chapters will show in detail what happens to each system in our bodies during this journey. How our bones become brittle, our muscles atrophy, our hearts shrink, our eyes change, and our brains are damaged. You will understand why the first humans to travel to Mars have to stay there. When we think about the dangers of a Mars mission, we might imagine technical malfunctions or meteorite impacts. But the deadliest threat is invisible. Cosmic radiation that bombards astronauts at any moment, altering their bodies at the cellular level. Here on Earth, the magnetic field and the atmosphere protect us from 99.9% of this dangerous radiation. In space, however, astronauts are exposed to a dose of 870 to 1,200 millisieverts, about 700 times more than on Earth. That's equivalent to 632 CT scans, or 12,000 X-rays, in just 2 to 3 years. The consequences are devastating. The risk of cancer increases by 5 to 10%, the cardiovascular system ages by decades, and the brain suffers measurable cognitive damage. Memory problems, slowed thinking, and difficulty making decisions can become irreversible. The eyes also develop cataracts prematurely, and the immune system is weakened by damaged bone marrow. Conventional shielding is ineffective. Thick armor even generates dangerous secondary radiation. A body exposed to this level of stress for years is fundamentally altered. The radiation is the first domino in a chain of physiological problems that increasingly make a return to Earth impossible. While the radiation invisibly does its work, something equally dramatic is happening simultaneously to the astronauts' skeletons and muscles. It is a gradual process that worsens month by month and represents perhaps the greatest barrier to returning to Earth. For what happens to our bodies in weightlessness is essentially accelerated aging, only it unfolds not over decades, but over months. Our bodies are a masterpiece of evolution, perfectly adapted to life under the constant strain of Earth's gravity. Every step we take, every movement we make, exercises our bones and muscles. Gravity is the invisible enemy our bodies fight against every day, and it is precisely this struggle that keeps us strong. If we remove this load, the body literally begins to disintegrate. The figures are alarmingly clear. Astronauts lose about 1 to 3% of their bone mass per month in weightlessness. That doesn't sound dramatic at first, but let's extrapolate. After 6 months, that's up to 18%. After a year, up to 36%. A Mars mission lasts at least 2 years, so we're talking about a potential bone loss of over 50%. For comparison, a 70-year-old woman with severe osteoporosis has lost about 30 to 40% of her bone mass. A Mars astronaut in their 30s could have the skeleton of a seriously ill elderly person after the mission. The weight-bearing bones are particularly affected: the hips, femurs, and spine. These are precisely the structures we desperately need to stand and walk on Earth. The underlying mechanism is insidious. In weightlessness, the body registers that the bones are no longer being stressed and interprets this as a signal that they are no longer needed. As a result, the body drastically reduces bone formation, while bone resorption continues at full speed. The calcium from the degraded bones is excreted via the kidneys, a process that also dramatically increases the risk of painful kidney stones. But it's not just bones that are wasting away. Muscle mass follows a similarly alarming pattern. Without the need to work against gravity, muscles atrophy at a frightening rate. Here too, we're talking about a loss of 1 to 3% per month. The leg muscles, back, and core muscles are particularly affected. Precisely those muscles that keep us upright and enable movement. What happens at the cellular level is both fascinating and disturbing. The muscle fibers change from slow, endurance-oriented type 1 fibers to fast type 2 fibers. This might sound advantageous at first, but these fast fibers also fatigue more quickly and are not designed for the kind of sustained activity required for life on Earth. Astronauts report that even simple tasks like climbing stairs become an ordeal after returning from missions on the ISS. In addition, there are problems with the joints. Without regular stress, cartilage and tendons also lose their structure. The cartilage, which normally acts as a shock absorber between the bones, becomes thinner and more brittle. This increases the long-term risk of osteoarthritis, not just in old age, but even at a young age. The International Space Station has taught us how serious this problem is. Despite intensive training, astronauts on the ISS have to exercise for 2 hours daily using resistance bands and treadmills. The deterioration can only be slowed, not stopped. And even after returning to Earth, it takes months, sometimes years, for bones and muscles to recover. Some astronauts never regain their original bone density. Herein lies the real dilemma of a Mars mission. The journey doesn't last 6 months like an ISS stay, but at least 2 years. Of that time, the astronauts spend 6 to 9 months in complete weightlessness on the outbound flight, then about 18 months on Mars at only 38% of Earth's gravity. A level of stress that is probably insufficient to stop the deterioration, and finally, another 6 to 9 months in weightlessness on the return flight. After such a period, the body is fundamentally altered. The bones are porous and brittle, the muscles weak and flabby. A return to full Earth gravity under these circumstances would not only be painful, but potentially life-threatening. The risk of bone fractures would be extremely high, even when simply trying to stand up. The heart, which is also a muscle and which we will discuss in the next chapter, would likely be too weak to pump blood upwards against gravity. The gradual deterioration of bones and muscles is therefore not a temporary inconvenience, but a fundamental barrier. After 2 to 3 years in space and on Mars, the human body is no longer built for Earth. It has become a Martian body, incapable of functioning in the environment for which it was originally designed. While bones and muscles atrophy, an equally dramatic change takes place in our most vital muscle, the heart. On Earth, the heart must constantly work against gravity to pump blood to the brain and upper body. This constant strain keeps it strong and efficient. In weightlessness, however, this need disappears, and the heart begins to shrink. Studies show that astronauts' hearts lose up to 20% of their mass during extended space missions. They literally shrink and weaken, like a muscle that hasn't been exercised for months. At the same time, the entire circulatory system changes. In weightlessness, blood rises, pooling in the head and upper body, hence the typical puffy head phenomenon, where astronauts develop puffy faces while their legs become thin like chicken legs. The body interprets this fluid shift as an excess and begins to excrete water. Blood volume drops by up to 20%. The heart adapts to this new, reduced workload, to the detriment of a later return to space. Because what happens when this shrunken, deconditioned heart is suddenly exposed to full Earth gravity again? It has to pump against a much greater resistance, but it only has a fraction of its original strength. Astronauts who have spent time on the ISS suffer from orthostatic intolerance. They become dizzy, their blood pressure drops, and some even faint when they try to stand up. After 2 to 3 years on a Mars mission, this effect would be drastically amplified. The heart would have adapted so much to the reduced gravity that a return to Earth's gravity would overwhelm it. Added to this are the aforementioned radiation-induced cardiovascular damages, calcified arteries, damaged blood vessels, and an increased risk of stroke. A heart that hasn't had to work against Earth's gravity for 2 years is no longer capable of performing this task. It has become the pump of another planet. And this is precisely the brutal reality. A Mars mission lasts at least 2 to 3 years, and during this time, the body changes so dramatically that a return becomes virtually impossible. The reasons are terrifying. Cosmic radiation, 700 times stronger than on Earth, causes irreversible DNA damage and a dramatically increased risk of cancer. At the same time, the body loses up to 50% of its bone density, comparable to severe osteoporosis. Muscles atrophy, especially in the legs and back. The heart shrinks by 20% and becomes too weak to pump blood against Earth's gravity. Although scientists are working on solutions like artificial gravity, none are ready for deployment. Therefore, only a one-way mission remains. Astronauts must be prepared to stay forever, not out of a thirst for adventure, but because their bodies compel them to.